Thank you everyone for joining me for this last part of the Binomial Theorem video. I have already presented part 1 and part 2 of the Binomial Theorem videos. And as you remember, I started the initial 2 videos with a basic expansion of a series which looks something like this. It was a symmetrical binomial in terms of the coefficients of a and b. We then went on to add coefficients with regards to a and b. We had like a coefficient here that's used as a capital A, and we had a coefficient here, capital B. We kept an exponent. Then we went onward to put a minus sign over here. Today I want to take the expansion of this binomial theorem to one step further by adding exponents within the parentheses. So I'm going to have exponents which will be impacted by the outside exponent. It will by no means spoil the symmetry of the exponents you will see, but it will create a multiplicative factor. And by multiplicative I mean in terms of multiples. You'll see a multiple effect which will kick in when we put in exponents for a and b. So the form of this expansion that I want to show you, it would look something like this. You would have, and I'm putting a plus minus because it can be either a plus or minus within the binomial. And the only reason here I'm adding capital A's and B are to show that there are coefficients impacting the A and B of the binomial. And then the x and the y represent inside exponents. The n, of course, as you remember, represents the outside exponent n. So if you have something which looks like this, how do we go about expanding it? Well, the answer is easy. It's pretty much the same set of techniques. And remember, think back to what this means. NCR, the combinatorial coefficient, it's represented by the NR in parentheses, which equals into n factorial divided by r factorial and divided further by the difference of n and r factorial, n minus r factorial. So let's just present a single example, and that'll be the end of this video. I want to show you a single example, but slightly more enhanced in terms of difficulty. And here is our example. We will do 2x, and of course I'd rather use a minus sign because it just adds a certain degree of difficulty, to the power of 3y, all to the power of 5, and we'll have a exponent 2 here and an exponent 3 here. The first thing we're looking at is this n value, which we use in an n plus 1 format to see that there are 6 terms. When we open this out, we'll have 6 terms. So let's start this expansion. We're going to do it using this format right here. We're going to start from here and we'll go across. So the first one, remember the first n value is always 5. And you'll see this 5 will stay across. In terms of this format, the 5 and n will stay. But the r value you always start out with is 0. Because this r value will work its way up to 5. See, the r will work its way up to 5, then you know your expansion is completed. Here's my a, here's my b. Remember, the minus sign is not part of b, it's part of the binomial. Let's do this, 2x squared. Remember, the first exponent here is n minus r. 5 minus 0, we'll put a 5. The next b terms, 3y to the power of 3, and let's make a little bit of space over here. The r exponent here is going to be 0. Remember, a minus means a plus minus alternating format till it's completed. We started with a plus, we put a minus here. The next term, remember 6 terms in total, we're on term number 2. We're gradually increasing the value of r, 1 each way, 1 each time. The inner items are going to stay the same, the exponents will change as we go across. Here the exponent of the a term is always n minus r, 5 minus 1, 4. The b term, we have 3y cubed. Here it's always r, which happens to be a 1. Let's put a plus sign because we're alternating signs. Let's go to the next term. You can imagine this will be a 5 and a 2. A term will become a 2x squared exponent n minus r, 5 minus 2, which is a 3. And you can imagine what this will be, 3y cubed to the power of r, which here is a 2. Remember, this 2 ends right over here. Our next term is going to be a minus because it's plus minus plus and then minus. Here we will have a 5 and a 3. 5 and a 3. And the a term will be 2x squared. I'm getting a little sloppy here with my handwriting, but the exponent here is n minus r. 5 minus 3 is a 2. And then this B term is 3y cubed to the power of r, which happens to be a 3. You see this r is gradually increasing from 0, 1, 2, 3. But I'll show you what that multiple effect I was showing you. When you open it up, you'll see that multiple effect. Next term, 5 and 4. 5 and 4, and then 5 and 5, we're done. 2x squared to the power of n minus r. 5 minus 4 is a 1. And then 3y cubed to the power of r, which is just a 4. Lastly, minus the final term, 5 and 5, n and r. When n and r equals are the same, we're done. We just have to finish this one last term. 2x squared to the power of n minus r. 5 minus 5 is a 0. 0. And then 3y cubed to the power of r, which is a 5. So now we have the task of actually opening this out. And we want to open this out so I can show you how your final answer will look. But you will see there's, in terms of just looking at these NR values, these NR 5, 0, 5, 1, 5, 2, they are symmetrical in terms of the Pascal numbers. If you do 5, 0 and 5, 5 in terms of this formula, you'll get exactly the same answer. And the answer over here will be just a 1. 5, 1 and 5, 4 will be exactly the same, because when you open them up, they'll be exactly the same numbers. 5, 2 and 5, 3 will be the same as well. But let's expand all of this. Let's do all of these calculations. As my first term over here, I'm getting 2 to the power of 5 times 3 to the power of 0. 2 to the power of 5 is 32. So I'm getting 32, and you got to remember the laws of exponents. X squared to the power of 5. This is 2 times 5, not 2 plus 5, 2 times 5. So you can have x to the power of 10. You know the exponent of 10 is going to gradually go down to 0, and your y exponent is going to gradually work its way up from 0 to whatever number, but it's going to work its way up. The next term, minus, we're going to calculate this right here on our calculator. It'll be 5 factorial, which is 120 divided by 4 factorial. I can do some of these combinations in my head. So you're going to end up getting a 5 over here. 5 times 2 to the power of 4, which is a 16, times 3 to the power of 1, I'm getting a 240 over here. I'm going to get 240 x to the power of 8 and y to the power of 3 times 1, 3. Next term right here, 5, 5, 2. It means 5 factorial divided by 2 factorial and divided by 3 factorial. That's 120 divided by 2 divided by 6. This right here equals a 10. 10 times 2 to the power of 8, 2 to the power of 3, which is 8. 10 times 8 is an 80. 80 times 9, 720. So 80 times 9 is a 720. I'm getting a 720 here as my coefficient. Let's solve the exponents. X squared to the power of 3 is x to the power of 6. And y cubed to the power of square is y to the power of 6. Let's put a minus because we're here. 5, 3 is going to give you exactly the same coefficient, except but these values here will remove the similarity. But let's do this. 120 divided by 6 divided by 2, that's this, which is a 10, times 2 to the power of 2, which is a 4, times 27, which is 3 cubed. I'm getting a 1080. Remember, we're losing the symmetry of our coefficients here only because these two numbers, a and b coefficients, are different. Otherwise, you would have had symmetrical numbers. Let's get the exponents in here. We have x to the power of 4 and we have y to the power of 9. This term right here, 5, 4 is a 5 factorial divided by 4 factorial and 1 factorial. That's 120 divided by 24. I get a 5 over here. 5 times 2 to the power of 1, which is a 10, times 2 to the power of 4, 81. I get an 810 over here. Let's get the exponents in here. And the exponents over here will be x squared and y to the 12. See, 3 exponent to the power of 4 is a 12. 3 to the 12. I'm going to come over here in case this part of the screen gets cut. This is my exact last term, minus. I'm right over here. 5 factorial divided by 5 factorial, 0 factorial. This whole thing right here zeroes out, but not into 0, but it becomes like a 1. It zeroes out to a coefficient of 1. We're only solving this part. 2 to the power of 0 is 1. Then we are left with 3 to the power of 5. 3 exponent 5 should be, I believe, a 243. Yeah, it's 243. And x squared to the power of 0 is 1. Y cubed to the power of 5 is y to the 15. So this right here is my final answer. But I want to show you the multiple exponent trend we're seeing here. Look at the coefficients are not symmetrical because these two numbers were not symmetrical. But these combinatorial coefficients would indeed have been symmetrical were it not for these two coefficients. But let's look at the exponents only for x and y. You'll see there's a multiple trend over here. x's will decrease by multiples of 2 until they go from the highest amount to 0. The highest amount is 5 times 2 is a 10. See, 5 times 2 is a 10. X worked its way from 10 by factors of 2 all the way up to 0. See, 10, 8, 6, 4, 2, x to the 0, and it's zeroed out. Y will work its way from the exponent of 0 all the way up to 15. 3 times 5 is 15, but it'll work its way up by multiples of 3. And look at that. You're seeing here y to the power of 0, but it's going to increase by 3's. 0, 3, 6, 9, 12, up to its highest multiple exponent of 15. So you can see here, when you have asymmetrical binomials, you lose the coefficient symmetries, but when you also throw in exponents in within the binomial parentheses, you add in this multiple effect. And that multiple effect is rather symmetrical in terms of individual exponents. So this right here is an complete expansion of this example, and I wanted to end the binomial theorem videos with this version of an example where I had exponents thrown in within the main exponent. So you can see the complete expansion over here, and it seems to me to be a correct answer. Exponents seem right, the coefficients are right. Well, I hope you all enjoyed this video. Please feel free to look over this video and the previous 2 videos several times to get the concepts clear. But please subscribe and like and share with your friends. Thank you and have a nice day.